Alright, on to another fun number theory counting AIME problem, 2016 AIME 2, question 8. Find the number of sets A, B, C of three distinct positive integers with the property that the product of A, B, and C is equal to the product of all of these. And so they're distinct positive integers, which means I'm going to look at the prime factorization of each of these. So 11 is already prime. 21 is 3 times 7. 31 is prime. 41 is prime. 51 is, let me see, I can take out a 7 from, wait, hold on, not 7, 17 from that, and I'll get 3 times 17, and then 61. Okay, so rewriting this, when I multiply all these together, it's the same as multiplying 3 squared times 7 times 11 times 17 times, I don't have 21, but I still have 31 times 41 times 61. And so here is what we're going to do. I have three numbers. So I have three things, A, B, and C, that I want to get spaces between. I have a few options. So looking at the 3 squared, there are 6 ways to permute that. I could have both of the 3's here and these having neither one. If I don't have any 3's, it's just 1. I could have a 3, and a 1. I could have a 3, so I could have 1, both of the 3's here, and a 1, a 1, and both of the 3's. Or I could have a 3, and a 1, a 3, a 1, and a 3, or a 1, a 3, and a 3. And you see 1, 2, 3, 4, 5, 6 ways to send the 3's through all of these. Okay. Now, for the rest, let me clear that junk out. Okay. So everything else, I have a few options, and I can send, let me get back to drawing ink, okay, lovely. I can send each of these to any one of the 3 numbers. So I have 3 choices for 7, 3 choices for 11, whether it's in A or B or C, 3 choices for 17, 3 choices for 31, 3 choices for 41, and 3 choices for 61. So that is 3 to the 6th power, which same thing as 9 times 9 times 9. 9 times 9 is 81, times 9 again is 729. Just easier way for me to look at it, because I might know 9 cubed, I might not automatically know 3 to the 6th. And when I include the ways to assign the 3's to A, B, and C, I have 6 of those. So that's 6 times 729. But here's the problem now. A lot of these are overcounted. And when I first started this problem, I just thought, okay, well, they're all overcounted 6 times, because we have A, B, and C here, and A, B, or C can be permuted 6 ways, 3 factorial. It can be ABC, ACB, BAC, BCA, CAB, or CBA, the 6 ways. So I thought, okay, well, I'll just divide this by 6. But there's a problem. And the problem comes in here. So there's a set of things that doesn't show up all the same. So in here, that's the case where you have everything in one of these sets, and that does not show up the same number of times. So in here, oh, I guess there are two of them. So everything and one other. So the case where we have everything in one of the sets, so I have everything here, sorry, that looks like a 0. I have everything here, and those are both 1. Or I have this one, everything here, this one. Or these two, and everything here. And so this doesn't actually show up 6 times, it only shows up 3 times. And the same is true for when I have the 3's spread out without anything else. So if this is just 3, 3, and those are the only factors that get sent to A and B, and everything else is sent here, or 3, y, and 3, or y, 3, and 3. And these don't show up 6 times, they show up 3 apiece. Okay? And the biggest problem here is they're not distinct. In this case, if I send all of these factors to one of the spots, the other 2 are 1. They're not distinct. If I only give 3 to 2 of them and have every other factor in the third, the 3's aren't distinct. So 3 and 3, I actually overcount 6 things. And then I have to divide out the 6 for the repetition by 3 factorial, because ABC and ACB should be the same. And so I just go through this. I can divide out the 6 through everything, and so I will get 729 minus 1, which is 728. Alright, any questions? Put them in the comments below. I hope I didn't get too sort of turned around when I started explaining this.